Hi, Ian. Welcome back to Airhacks FM.
Oh, thank you.
And today, we would like to turn back time, or at least you had some ideas. And you said last time you mentioned a little bit that Java went in a wrong direction. So why and what's your ideas?
So I think one of the things that Java really did well when it came out were its APIs. So back in like the mid-90s, I started writing Java code on Java 1.4. And the equivalent Microsoft manual or STL manual to what Java had was usually like, 3 or 4 times the size. And it lacked clarity, it wasn't succinct, and so on. So Java did really well with its APIs, but different people have been pushing it in different directions over time. So I think it might have been Java 7 where they changed the behavior of string substring. Okay, so like string substring doesn't sound like it's a big deal. But it used to be back when Java 6 was the thing that people could do things like read an entire file into a string, and then they could get sentences and they could get words from that file by substringing that very big string that they had initially. Okay, and the change that happened was that substring would start to clone the string. It would copy the contents with it. And so you went from substring having this kind of order one behavior where you could generate a substring and all it would do is create this little wrapper object for your original character array. And the behavior changed to this kind of order n behavior where you'd end up copying every single character for the substring. And if your code base doesn't use substring a lot and doesn't rely on this like very cheap substring behavior, then you're going to get away with that. But it turned out that there were certain things in Google that the performance regressed so significantly from that one change that we had to go and go and change things. And if you look at kind of like
how you change things, you implemented your own substring.
That could be one way. Look at what the code was actually doing and then go and fix it. And I think one of the problems that Java had initially was it didn't have any customers because it was a new thing. And so if you're a new thing, then how do you design what you're going to do because you don't know what your customers are going to do? So an example of that is the Jack parser. So with the Jack parser, what they do is they match a token, much like Lex would match a token. And on having matched a token, they then throw an exception. And this kind of like violates the principle that exceptions are exceptional.
Absolutely. And actually all design principles that even exception must not control the flow of the program, right?
Right. But back in 1998, when Jack was chosen as a standard Java benchmark as part of SpecJVM, it didn't seem like an unreasonable thing to do. And because of that, SpecJVM 98 numbers are kind of skewed to make JVMs that throw exceptions quickly. It will make them look very fast on the Jack parser. And that could turn out not to be a useful thing for the JVM.
Jack parser? What do you mean by Jack? What is J?
JACK. It's an old thing. It was part of the SpecJVM 98 suite. I don't think it was widely used. I think ANTLR, another tool for language research, is kind of like the thing that people
Antler. I know the Antler.
Yeah, so people use Antler these days, but kind of very early on there was a parser called Jack. And the only curious thing about it is that it used exceptions for saying here's a token. But Jack,
like the first name, right?
Yes, Jack and the Beanstalk. But there's a similar thing with class loaders. So class loaders have been there since the beginning of Java, and some people say that using class loaders is one of the most novel feature in Java. The fact that you pair a type with a class loader, and it's kind of a runtime notion. And when you don't have a class, the class not found exception gets thrown. And why would that matter? Well, there are benchmarks out there like Tcapo, and what they do is they do this trick like a Russian nesting doll, where they put a zip file inside of a zip file inside of a zip file, and all of those zip files, those jar files, are going to throw class not found exceptions. And so what you find is that the Tcapo suite is more of a benchmark of the ability to throw exceptions than it is of the actual underlying benchmarks.
Back to the jack, because I got interested now, and this jack is with double C, right? GACC.
Is it? I thought it was.
Just another compiler for Java.
Well, I'm thinking of the one that's in spec JVM 98.
Maybe it's that, but what I used back then, or not, was Yak with Y.
Oh, yes, but that I don't think that really had a Java backend to it.
And interestingly, there's a jack with just another compiler for Java, and this is based, including Carp, Antler, Java CC, Sable, Cocoa, BYACC, and Jikes parser generator even is related to this. So, and this is Portland State University. So I can give you the link right now. And I heard about Yak. I was confronted with that in a project. Antler as well. And there's a Jikes parser generator. You know this? Jikes parser.
Well, I worked on Jikes RVM, of course.
Yeah.
So anyway, we started off talking about strings and got distracted. And so the thing with string is that substring was defined to return a string. And the effective Java 52, I think it is, says that you should use interfaces instead of like implementation types. And so your function should return a map. It shouldn't return a hash map. Your method should return a map and not a hash map. So that then you can go and change the implementation to not use hash maps. And the fact that substring returned a string meant that you then didn't have a choice on how you were going to implement substring, where one implementation could be, let's have a string and an offset and a length within that string. And one implementation could be copying the whole thing. And so, there's lots of things wrong with string. And so the primitive.
But there is something similar to interface. It's called CharSequence, right?
Yeah. So substring could have been defined to return a CharSequence. Now, normally in programming languages, if you're typing more characters, you're being penalized. You're doing something wrong. It's kind of like a rule of programming languages. And so I would argue that maybe CharSequence should be what we think of as string today, and string should really be the interface that CharSequence is.
And CharSequence was introduced in JDK 1.4, interestingly.
And one of my gripes with CharSequence is we have a thing. There's a set of libraries called Guava, GUAVA, and they provide a thing called a rope. So you come across ropes or
no? But Guava. So Guava was very popular as a Google library. Rope.
So what a rope is instead of having a string where you've kind of like concatenated everything into a giant array, what a rope lets you do is have like a collection of char sequences where one char sequence appears after another char sequence after another char sequence. And this is very convenient because you don't need to kind of like get all of that memory straight away. But the ropes itself in Guava don't implement char sequence. And the reason for that is that Java made a decision that the length of a string or length of a char sequence should be an integer. And that limits it to 2 to the 31, 2 gigabytes worth of string, and we want ropes to be bigger than that. So again, a decision which was made kind of like pragmatically in the 90s, like having length be an integer, probably today it would make sense for it to be a long.
Yes. I think today everything would be long, in which returns a length or something like this.
Right. So,
but it's not a bad decision. I think the decision would be even made again, right? If we could turn back time and we had the same computers, the same environment, I think with the constraints from back then, int was the right choice, right?
I'm in two minds about it.
Okay.
Like I do a lot of C programming, a lot of C++ programming, and Google's coding style recommends using signed types for everything. Okay. And in C, there's a popular strlen function that's going to give you the length of a string, but it returns an unsigned type. And if you look in J and I, then the array length is actually given to you in a thing that they call a J size, which is an unsigned integer. And so clearly one set of people, when Java was being created, were thinking, well, it doesn't really make sense to have negatively sized arrays. And I would kind of go along with that. The other camp, the people who are putting into Google's coding style, you should use signed integers. What they're worrying about is when you go, if you go through an array backwards, and you're decrementing instead of incrementing a counter, that is quite easy to screw up the termination condition. So you can make an unsigned condition which would never terminate, because you'd say, is it less than 0? Now, teaching compilers to warn about comparing unsigned values to less than 0 is pretty straightforward. And so I don't think that's a legitimate concern. Okay. And the fact that we made, all of the Java arrays and strings and so on 2 times smaller than they need to be, that seems unfortunate. And, so there's lots of weird things. It's things like, byte in Java is signed and chars are unsigned. There's lots of little weird things in there. We've got char as an unsigned 16-bit value, and we've got short as a signed 16-bit value. So why have we got those two in a signed and an unsigned variant?
You know why?
Sorry.
You know why, or you? Think
I don't know why.
Okay.
I'm sure people like Josh will, Josh Block will justify it, but it seems that there were different thought processes going on, and there always are. And at some point, you have to go, okay, well, this is the thing that we're going to release, and so they released it. The one which I wonder, with hindsight, is the bigger misstep is StringBuffer and StringBuilder, and everybody's been taught that, if you do Java, you should load StringBuffer. Only an old fuddy-duddy would use StringBuffer, and all of the hip kids would use a StringBuilder.
Yes.
Because no locking, it's going to be way faster.
Yeah.
But when you use a StringBuilder, the toString, so the whole point of using a StringBuilder is to build a string. It's there in the name. Yeah. And you're going to get all of these char sequences, and you're going to whack them all into your StringBuilder. And then the last thing you're going to do with your StringBuilder is call toString on it. Okay? Now, because StringBuilder isn't synchronized, then the array that it's been creating for the string that it's going to create is not protected by any kind of locks. And so somebody on another thread could append to that StringBuilder and could also call toString. Okay? And if you allow the ownership of the character array to pass to the string, and if you're doing fancy string implementations, you can do similar tricks, then there's a race condition introduced. So what StringBuilder does when you call toString is it copies its entire array into a new array, it clones it, and then it passes ownership of that onto the string. Okay? Whereas with a string buffer, because that's guarded by a lock, then you can just pass the ownership of the underlying character array to the string. And everything's guarded by locks and everything's clean and simple. And, the reason that was done was that locks were expensive. Okay. But we could have fixed the problem of locks as being expensive and avoided doubling the amount of RAM we need to use. And
so what you're saying is that nowadays, if you are single-threaded in a single-threaded program, actually StringBuffer should be faster than StringBuilder.
Well, if you're single-threaded, then the hope would be that the biased locking would determine that, and biased locking's gone away in the newer JVMs, but biased locking would work out that, hey, these locks are being taken, but they're never contended. And because there's no lock contention on these things, then we can just kind of, what biased locking does is you atomically say, hey, I'm biasing this lock to this thread. And this thread effectively now owns the object. And if anybody else wants to take it, it's an expensive operation. But the hope is that once you now own the object, any locking and unlocking operation just becomes a check. Do I still own the lock? And if you still own the lock, then you just go, okay, I don't need to do anything. No atomic operations, no anything. And so the decision to go from string buffer to StringBuilder in the language meant the optimizations in the JVM, like biased locking, well, what's the point of them so much? Because that would have been your killer use case. And because people are writing the code differently, then we're now in the situation where we're using a lot more RAM than we used to. And things like substring, where the behavior changes, and it could be that you're heavily reliant on that previous behavior.
But using memory means also it takes some time. So StringBuffer has to be faster than StringBuilder, right?
Well, it depends on the cost of the atomic operations for the locks. Yeah, but yes, it should be. Yeah.
So if it's reasonably implemented, but in single-thread environment, StringBuffer should be faster than StringBuilder. And in a multi-threaded environment, StringBuilder is concurrent and StringBuffer will be
the
locked.
StringBuffer is the concurrent one. So StringBuilder.
StringBuilder is the old one.
StringBuffer is the locked old one.
Yeah, StringBuffer is the old one. So if multiple threads will access the StringBuffer, then there will be contention, and StringBuilder will be concurrent.
Well, but in practice, there never is any contention, so you can optimize it away. But the StringBuilder has pessimized things because I used to have this idea that I threw around for hopefully for a grad student to pick up, was that Java suffers from this thing that I called attack of the clones. So because you don't know how somebody's going to use something in the future, and you can't prevent it by saying, hey, I'm going to give you a const version of this. The only safe thing to do is to clone. And then now that we've got this attack of the clones problem, what can we do to optimize that in the runtime? So can we spot these clones which are unnecessary, and then kind of like infer that this use of this clone is essentially a const use of this clone, and then in the JVM we can go like, okay, well we'll elide this clone operation. We can just pass through the original value. It's safe.
So your idea would be to make the locking more efficient instead of cloning, right?
Yeah, there's been a lot of work. The hot thing, kind of 20 years ago was transactional memory for looking at this problem. And so, yeah.
Yeah, and the transactional memory means that there is some cloning, but efficient one, right? So you can
one way of doing transactional memory in hardware would be to say, when you have an exclusive cache line, that you effectively own that cache line. And if anybody else steals that cache line, then you abort your transaction.
It means in software means if you will emulate that we have a single region, but if someone would like to write, we will copy the region, right?
Yeah. So it's tied into kind of like choices in programming languages like copy on write.
Exactly.
So Swift had copy on write.
And copy on write array list we have as well, I think, in Java, right?
Yes, which is a concurrent collection. So, yeah.
So what means is that the old readers will see the old stuff until they are done, and the new readers get the newer copy, right? So this would be in practice how this would work.
Yeah. So writing could be incredibly expensive if there are readers.
Yeah.
Yeah. There are even more bizarre things that people do. So I work a lot on the Linux kernel, and they have a thing called read copy update, where you try to use like the scheduling of threads as a way of saying that this thread was in a particular epoch, or tasks as they get called in the kernel. And when epochs change, then you can say that threads could see old or new values, or they generally just see old values if they're in an older epoch, and so on. Once you know everybody's in a new epoch, then you can do things like garbage collect memory that they were looking at.
So you can switch in your thread during lifetime of the thread between two epochs, or you have to do it upfront in your kernel?
So the movement to the next epoch is actually handled by the scheduling in the kernel. And you can create these regions where you say, I don't want my epoch to change, and you basically set yourself to be unpreemptible in the kernel, and so on. But these are kind of like efficient ways. They're very efficient, but they're under this premise that kind of like the memory you're going to need to reclaim is very limited. And it could be that if these are network buffers, then people can allocate network buffers very quickly. And then all of a sudden you're in this kind of like garbage collection problem that you see in Java and so on.
But this is unrelated to Java, right? This is just what we are talking about. This epoch is just...
Yeah, people can try and do exotic garbage collectors using these things, but I'm not familiar with anybody who's actually done that.
This could be actually a leisure job, right? Vacation something, so a nice garbage collect.
Well, I've written some well-known garbage collectors.
Okay, which one you wrote?
So I was heavily involved in a garbage collector called C4.
Ah, okay.
Which is Azul's garbage collector. So Azul were doing the transition away from their own custom hardware to x86. And when you've got your own hardware, you can do, fancy things, like they had a read barrier instruction. When you move to x86, you've got to think, how can I do the same trick in an efficient manner? And so the standard read barrier that C4 used, which is now used in ZGC and Shenandoah, was my invention. So I'm incredibly proud of it, because when you study computer science, you're taught what exclusive OR is. Yeah. But in practice, how many times have you actually used exclusive OR? Like next to never.
Yeah.
And this was a practical use of exclusive OR.
Okay.
So
first, what interests me, because you said you are proud about that, when you got the idea and where?
Oh, absolutely.
Under the shower, or where?
So I was working for Azul Systems, and I'd been nagging them for a laptop. And they gave me this ex-salesperson or something, whoever's laptop it was, they gave me this giant brick of a laptop. And it was Java 1 in the Moscone Center in San Francisco. And so from where I lived, I needed to take a train to go to the Moscone Center, and I didn't want to carry around this giant brick of a laptop. In part because the Moscone Center is not too far from the train station in San Francisco, but immediately outside the train station, it's a bit dodgy. And if I'm carrying around this giant brick of a laptop, then my spider senses were telling me that I was going to get mugged.
Yeah.
And so I knew that I wanted to work on, if you're working for Azul, the bread and butter is concurrent garbage collectors. And the biggest problem there is the read barrier. And so I took a pen and paper with me, and I was sitting down and thinking about the problem. And that's when on the train journey there, I'd figured out what I wanted to do. But I didn't have any means of doing it until I got back home again. That evening, I coded up the solution. And then the next day, I was at the Moscone Center talking to the rest of the Azure guys about the results that I'd got.
So you proposed that talk and you had no idea whether it would work?
Oh, no, I didn't have a talk at them. I was just attending Java 1 to be my usual annoyance and things like that. Actually, I've not been to Java 1 for a while.
Why usual annoyance? You didn't like Java 1?
Oh, no, I would usually... I think at that Java 1, there was a workshop, and one of the questions was like, what should we do next in Java? And I said value types. I was the first person who put my hand up and said value types. And the Oracle employee said, yes, we're thinking about those, and wanted to quickly move on because Project Valkyrie has taken a while to come together and to land.
Was it Oracle employee or Sun? This was sure.
It was Oracle when I came to the States. And yeah, so it was
after 2010, right?
I came around about 2009, so it could have been.
Because 2010 Oracle bought Sun, so I think around.
Yeah. So I always have this way of saying that everything comes back to Manchester in the UK. So we did this binary translator company, and we did Rosetta for Apple. And the next thing that binary translator company was working on, well, one of those things was a Spark to Power binary translator. So the back end was Power and the front end was Spark. And the company was acquired by IBM because IBM, of course, were going to buy Sun.
Yeah.
And the plan for the server business for IBM was that they were going to use the binary translator to migrate all of these Spark binaries onto Power, and they were going to consolidate the Power and the Spark server businesses. But that didn't.
It would be interesting what would happen, right? If IBM would bought by Sun, how different would it be?
Yeah. I mean, but that was the expectation that was going to happen, and then the Oracle thing really, caught a lot of people off guard. So, yeah,
it would be interesting, how it happened internally that all of a sudden Oracle acquired Sun. The backstory would be interesting.
Yeah. So. We're talking about read barriers and garbage collectors. So the observation for the C4 read barrier was that if you have something like a linked list, which you generally don't have in Java, but for the sake of argument, we say we have a linked list, then you could imagine that all of the nodes on the linked list are on the same page of memory. Okay? Yes. Now, I'm a big fan of kind of something which happens very early on in Brian Getz's Java concurrency book, where he says that the trouble with concurrent programming is shared mutable state. So if the state isn't shared and if it's mutable, then that's where you've got your troubles. So for the garbage collector, what you want to know is, do I have a copy of this object? So because you're moving objects in memory, the object could be in two places at the same time. And these days, what sane read barriers do is, and what Azul always did, was they maintain a two-space invariant, which means if an object could be in two places, then it's only in the kind of like the destination place that you're going to put it. So you've got this two-space invariant that whenever
Excuse
you have...
me, an object can be in two spaces because it's copied, right?
It's copied, yes. Yeah, so you could be copying it out of the nursery, into the old generation. Or you could be doing various copies. And you want to maintain this invariant that something is in the two space. There were garbage collectors like Metronome from IBM, where they tried to have a more complicated relationship, and then kind of like fix that up in generating code. But that's a bad idea. The two-space invariant's the way to go. And if you're going through a linked list, the normal things that Metronome and other people were doing were every time they loaded a pointer, they would then load through that pointer. So they would go and check either some metadata about the pointer and say, is it in a two space? So you could have a big table of where all your two spaces are, and you could hash the pointer and go and look it up in a table. Or you could put something in the object header, and you could go and say, does this object have the current two-space bit in it?
Excuse me, you say two space, so you're assuming there can be only two copies? Or is it like more than two?
So you have a from and a two space, but it could be that you have a from and a two space both for your new generation and your old generation.
Okay.
So there could be lots of things going on, but in general, you're just worrying about a from and a two.
Okay.
And you'd never have an object which was both in the new generation and in the old generation. And so the observation that I had was that it's very likely that all of these nodes in a linked list are all going to be on the same page in memory. And normally you want to do some efficiency and have things be page oriented. And so if you can tell that all of these things are on the same page in memory, then you don't need to do these expensive extra loads. So if you're iterating a linked list, it's kind of a worst case for a read barrier where you read through the read barrier because you're doing two loads for every node in the linked list. But also the second load depends on the value from the first load. Okay, so what we can do instead is we can load the pointer, and we want to go, hey, is this pointer in a two space? And we can check it against the pointer we loaded from. So we can XOR the two pointers together. And if they only differ in the low bit, then we know they're in the same page. So there's the use of XOR. And because XOR is a reversible operation as well, you can save a register if you really want to. But this is a trick for doing read barriers in concurrent garbage collectors, where you're not kind of like completely pessimizing the code.
If the pointers only differ in the lower bits, we know what that it is.
They're in the same page.
On the same page.
And then because you know the one you're loading from.
But if they don't differ at all, then
then you've got a linked list which is pointing to itself, and you're going to recurse forever, kind of going along.
Okay.
Yeah, but the point is that because you know the pointer you're loading from is in the two space.
I'm just I'm not that low level usually. So a page has like a memory from two, and the lower bits means we are within the page, right? Within the range. This is why you're saying only if they differ in the lower bits, it means that now we are on the same page. Because if they're higher than that, it would be outside the page, right?
Yeah.
It would be another copy, right? This is what you're talking about.
Yeah. And so, so this is what I did for C4.
And you XORed what? You XORed from and to, or what do you XORed again?
So you're loading from a pointer, and you're loading a pointer from a pointer from a pointer, a reference from a reference in the Java terms, and you know the reference you're loading from must be in the two space because you wouldn't be able to use it otherwise. And the question is the reference you load also in a two space? And you can check that by doing an XOR. Okay, and that means you can use computation to prove something that previously you'd always had to go and load from memory. So you've traded computation for memory accesses, but in the case of like iterating down a linked list, you're memory bound. You're waiting for these memory accesses all the time.
And I'm assuming XOR is a hardware accelerator. Is very fast, right?
It can be fast. Yeah,
it can be fast. Okay.
Yeah. I was heavily involved in kind of like the runtime and performance kind of aspects of what C4 was, and I would say that pretty much every garbage collector is now doing the same tricks.
But how you got the idea? You got the idea looking at the memory addresses, or
like I say, I didn't have a laptop with me. I just had a notebook.
Yeah.
And I had this idea that I'm doing things with pointers. And my original idea was that I'd have some kind of like algebra or arithmetic for pointers. Mm-hmm. And then from this, I could prove certain principles. So I wrote a little research paper about it, where like, if you're searching for a needle in a haystack of pointers, mm-hmm. And it could be that you search through the haystack and mm-hmm. you don't find a match. Mm-hmm. And it's only in that case that you then need to go and search again and do all of the read barriers. Because if you did get a match, then you knew that the two-space invariant held. Mm-hmm. And so if you're trying to elide all of these read barriers, then these can be tricks that you use.
Okay.
And so C4 was one of mine. And then kind of like the one that everybody's used is the Android garbage collector. Mm-hmm. So when I wrote art, the issue was that we were going to do ahead of time code compilation for various reasons that I shouldn't go into. But the problem there was, well, how much disk storage do we have? Uh-huh. So if we have DEX code and it's a megabyte, if we compile the DEX code and we need 100 megabytes, uh-huh. then there isn't going to be storage on the phone for that. So it's kind of ridiculous.
And DEX, you mean double-ended queue, or what do you mean by DEX?
So DEX is so in Java you have like .class files, uh-huh. and on Android you have .dex files.
Oh, okay. Uh-huh.
Uh-huh. And so we had to do this ahead of time code compilation. And so I created art and did all those ahead of time code compilation. But we wanted the garbage collector to have all the latest and greatest features. So why not do something similar to C4 that uh-huh. Azul had done? And the problem there is if every time you loaded a pointer, you had to generate all of these XOR and branch instructions and so on, mm-hmm. then you would go from one Dalvik instruction to maybe, a dozen ARM instructions, mm-hmm. Which was what kind of mattered at the time. And that would be unacceptable. Mm-hmm. So then you've got to think, well, what can we do which is as close to that, but without read barriers? Mm-hmm. And so it never got a name other than kind of like the garbage collector for art. But I did a thing which was a generational concurrent garbage collector. Mm-hmm. And so if you can move objects around, it's easy to say what's old and what's new. Mm-hmm. And you can separate memory into regions. But if you can't move things, it's difficult to say what's old and new. Mm-hmm.
You will need a table or something,
Yeah. And so there was an observation which was made in the 1980s that, and a lot of this stuff comes back to Hans Boehm and the Boehm.
I thought to Manchester.
No. This goes back to Hans. Okay. And so they had this observation that when you mark, so the thing that takes all the time in a garbage collector is marking the heap. Mm-hmm. So it's going and finding where all your live objects are, and then everything else by definition is free. Mm-hmm. Okay. And it's doing that traversal that takes all of the time. Mm-hmm. And which is kind of why garbage collector research is uninteresting. Mm-hmm.
Interesting or uninteresting?
There are academics who've made it their entire career, and this surprises me.
Okay.
They're very fond of saying, "Hey, we made something 20% faster," but what they really made was like this part of a subsystem of a subsystem of a subsystem. We made that 20% faster, and on a wall clock, you would never notice.
Okay.
So they're being honest, but if you were a user and you were expecting things to run 20% faster, you would find that they were dishonest. Okay. But it's a kind of a par for the course kind of dishonesty. So we were talking. So the trick that Hans came up with was that when you go and find all of these objects, you don't need to throw that information away. You can hold on to it. Okay. And so if you're keeping this information in a bitmap, where the bitmap summarizes what's in memory, then if you go and mark the whole heap again, then the new bitmap will tell you the difference between the new objects and the old objects. So the previous bitmap tells you about the old objects. And so the way that they called this is they called it being sticky. So if you remember the old mark state of an object, then it's somewhat sticky that you've remembered it, and that object is old. And so the trick that needed to be pulled off for art was, how do you have a old and a new generation, and at the same time you're concurrently allowing the threads to access the heap, and you're trying to perform things like garbage collection, where you want to prioritize doing new generation collections, because the adage that most objects die young is very much true. And if you can only scan the part of the heap where the new objects are, then you save huge amounts of time. And so when art came out in Android KitKat, which would have been 10 years ago, then it had a concurrent collector, but it was also generational.
Not that long ago, 2016 is actually, right?
Well, I joined Google in 2011, so there were versions that existed much longer ago than that.
But you wrote art and a garbage collector.
Yeah, so I kind of drove art to be what it became. Yeah, and as part of that was doing the garbage collector. And in fact, the original compilers for art were just repurposed ones from Dalvik, which I wasn't particularly keen on, because the Dalvik compilers were not the best. But it was an expedient thing so that we could get something out the door. And we put it in as a developer mode option in Android KitKat, thinking that nobody would notice. And then everybody was like, hey, here's this way to make your phone way faster. And everybody was like, oh, I've got to unlock the developer options. Oh, I've got to choose this. And so the first thing
how much faster was it?
Oh, it was a huge leap. So I was kind of disappointed we never launched on the original kind of like old Nexus 7. Because that was a device where you could really the problem was, because the hardware was getting better, then it was harder to see the performance improvements. On an old Nexus 7, it was night and day. So if you take something like Google Maps, and you just kind of like stroll around the tiles, you're just panning around on Google Maps, it turns out about half of what you were doing was doing interface calls. Okay. And the way in Java, you can have multiple interfaces per class. And so when you're trying to work out, hey, I'm trying to call this particular interface function, list.add or something like this, or list.get, then you have to go through all of the interfaces. And the way that was implemented on Dalvik was literally you iterated through a list of all of the interfaces. Okay. It's not hugely better in Hotspot. And, but the thing which fixes it for hotspot is it has polymorphic inline caches. Dalvik didn't have polymorphic inline caches. And so what Dalvik was doing for all of these interface calls was it was iterating through a linked list. But Dalvik joined lots of class files together.
I remember it was early Java. You could make classes faster by declaring them final.
That you could do that, or you could just return don't pay attention to effective Java 52 and return like the implementation type. So what Google Maps was doing is using interfaces. It was doing the right thing by effective Java 52, but it was spending all of its time iterating over these linked lists. But the problem for the linked lists was that Dex was combining all these class files, and all the interfaces were sorted alphabetically so that you could kind of like deduplicate and so on. And so what tended to be at the beginning of the list were things like abstract collection. And they never implemented the method you were looking for. So you usually ended up going halfway down the list of interfaces to find the interface you were after to then go and dispatch on the right method. The trick we did in
Z. You rename it to Z, abstract collection.
Well, yeah, right. The trick we did in art was that, and this is a trick from Jike's RVM, which is you make a hash map. The key for the hash map is the method and the class that you're trying to dispatch to, and you put that hash map directly into the equivalent of the V table or the class. And so you load from there. And the problem with hash table is you could get a collision. So two things could have the same. So when you know the interface and the method when you're creating the code to do the dispatch. And the problem is that you could find something where there's a collision. But if you've sized your hash table to be the right size, then the chance of a collision is very small. And so if you took something like Google Maps, which was running on this old Nexus 7, and it's spending half of its time just doing interface dispatch, and in art, what happens is you're just directly calling the code. There's no dispatch because you just load from the hash table and go. Then you suddenly get rid of what was taking half of the time on it. And then all of a sudden, Google Maps goes from kind of like, maybe 5 frames a second to like, 15 frames a second.
Wow.
It's, this huge like step up in performance. Now, in terms of the garbage collector, we went from fairly typical 50 millisecond pauses to kind of like 1 millisecond pauses.
Wow.
And 50 milliseconds would be 3 dropped frames at 60 frames a second, whereas 1 millisecond, you could be doing 100 hertz and 120 hertz displays quite easily.
What was the reaction inside the company? So if you introduce such an improvement, and this is a massive scale, millions of devices, I guess, was it like, the UI people were maybe, excited about new possibilities, or everyone was, delighted, or what? I mean, what does something happen, or no one notices, or what?
So I used to joke that the way that I thought we were going to get this stuff out the door was that CyanogenMod were going to realize it was there in AOSP, and CyanogenMod would end up launching an Android distro with this stuff in it. And then when they did it and they said that they were so much faster and better than regular Android, then the managers would have this aha moment and decide that they were going to switch over to it. So when you talk to, the people leading projects, project managers and product managers, and one of the things that they need to do is manage risk, okay? And changing the entire runtime for an operating system, if they did ask me, they go, is this a risky thing to do, Ian? And my answer was yes.
Yeah, of course, yeah.
So the story from Android KitKat was that people switched over to using Art, and the first thing that I broke was WhatsApp, and I didn't know what WhatsApp was because when I use Google Chat and I use all Google things for doing things, and people are going like, "Oh, you've broken WhatsApp," and so on. And I'm like, "What's WhatsApp?"
You said, who cares, about two users, right?
Well, WhatsApp had been bought, I think maybe the same year or the year before by Facebook, as it was then. I think it was more than 20 billion or something.
Yeah.
They paid a lot of money for it.
Because WhatsApp was huge in Europe, not that in US. Now it's back then, right?
Yeah. And what it was that WhatsApp obfuscates its bytecode. So they ran this really lousy bytecode obfuscator on it. And that bytecode obfuscator would inject instructions which said things like, if false, take a lock. Mm-hmm. Okay? And I'd put a thing into art which said that all locks should be balanced. Mm-hmm. Okay? So what balanced means is if you lock it, you need to unlock it. Mm-hmm. Okay? And the reason for doing this is if I want to do fancy lock optimizations like biased locking, mm-hmm. then the implementation of that really usually relies on the locks being balanced. Mm-hmm. And this bytecode obfuscator for WhatsApp was violating that. Mm-hmm. And so people were telling me, what are you going to do? And it was like, well, file a bug report with WhatsApp and tell them to switch off their lousy bytecode obfuscator. But people were like, no, you can't do that, Ian. You've got to go and allow WhatsApp to run. And it's like, well, this is a developer feature. But a lot of people with KitKat were using Art and so on.
Were you actually nervous back then before it was introduced because this scale was massive? Or you said, okay, it's just developer feature, I don't care? Or what was sleepless nights before the introduction of the feature?
Well, I mean, there's a lot of testing that goes on. Mm-hmm. And, everybody's kind of running it on their devices and so okay. on. I had a lot of experience. Mm-hmm. And so I made a lot of calls early on in how art was written that still hold up today. We were talking about type systems and string should be returning a char sequence and substring should be returning a char sequence. I've done research papers about, final and const. And how can we do something better than that? The thing that I did in the context of art was the Java heap. I modeled it with a reader-writer lock to use the kind of the Java language for it. So the Java threads were readers. They all wanted to share access to the Java heap. And the garbage collector threads wanted exclusive access. They wanted to have writer access to the Java heap. Mm-hmm. And a few years before, a guy called Leslie Hutchins had added thread safety annotations to GCC, and then he was working on the migration to Clang, to CLang, and LLVM. And so Art was the first thing building an Android which was using CLang because we wanted these thread safety annotations. And what we were using thread safety annotations primarily for was to say this C++ thread is accessing the Java heap. Mm-hmm. And you had to annotate this function holds the mutator lock, as it was called. Mm-hmm. And because of that, you couldn't be accessing the Java heap, say, go and do something else and then come back again and read from a stale pointer. Mm-hmm. So a stale pointer would be pointing to the old version of an object, mm-hmm. Or an object which is being garbage collected. And so thread safety annotations were a way of kind of mitigating this risk. And if you screwed it up, if a developer wanted to really access the Java heap, but they really didn't like to use these lock annotations, the compiler enforced it. The compiler said, no, your code doesn't compile. Okay. Now, you could have turned off the compiler warnings to get past it, but you would have had to be going some. So the normal thing in software projects is that people who put out fires get rewarded. It's like, you saved the company because you put out this amazing fire. But when we were doing art, it was an incredibly small team, largely just me. And so because of that, I had to think, well, I don't scale. How do I make it so that I don't keep, shooting myself in the foot? And thread safety annotations were a big step towards that, because I had experience from lots of other runtimes that the usual way that these things break, and so on. And it wasn't as if Dalvik was bug free. But
so you can say that you are the smallest team at Google, right?
I wouldn't say
that's the smallest. 1-person team is very small.
One, it wasn't one person. The thing is like it changed. So the team now is far bigger than it was when it all started off, and there were other things going on in the company because of that. The lawsuit was a big worry, and maybe we needed to do whole new programming languages to avoid the lawsuit and things like that. So art was this thing that I did, that eventually everybody was like, so you were saying like, what were people's reactions? Well, the graphics people, they started using it, and they were just saying to their managers like, I've got all of these bugs about jank and things not being smooth and everything else like that. But if we switch the runtime from Dalvik to art, it's all fixed. Yeah. So it's like, I can close all my bugs if we do this one transition. Yeah. Please, can we do this transition? So the product managers who were saying, hey, if we do this, it's huge risk. They were like, oh, well, I'm getting all of this pressure now. But even then, it's like, you can't kind of like assume that common sense will just happen.
Yeah, exactly. This is what in larger companies always the case, So this is, What's another question, because you are working on Linux kernel right now?
Yeah.
And the question is it as boring as compilers, or as exciting as Java? So is it like, are there completely crazy ideas in Linux kernel what you could achieve? Or is it more like, a small improvements? It's more like, incremental improvements, and at scale of Google, you can improve a little things, and at the scale, there are huge gains.
So my thing at the moment is, if you think about, you get that phone call, please come over and help me fix my computer. And the first thing that you do when the person's computer is running slowly is you run Task Manager, or on Linux you would run top or something like, and you try and figure out what's this computer doing. And these days you're probably spending more money on your GPU than your CPU. And so you don't really understand what's going on in your computer. Task Manager will give you a little graph of GPU load and CPU load, but you can't really see what tasks are using the GPU. And so we kind of have very crude tools for doing this. And so I've been working firstly to turn like the perf tool into something, the Linux perf tool into something that works. It doesn't just crash all the time. Okay. But then the other aspect of that is to broaden what it does, so that it becomes this place that you can go and answer these questions about what's going on in the system. And I'm very excited about that, because all of these tricks for making garbage collectors faster and this, that, and the other. If you look at kind of like what happens in literature and in the real world, is people will make a change and then they'll measure it with their watch, and they'll go like, oh, I saved a second. Okay, that's a good thing. Therefore, it must be down to my change. And it could be that the change you made suddenly used less disk or something, and it could be that the savings really coming from that. And maybe if your disk wasn't as full or something like that, then that would have an equivalent performance saving.
So you cannot prove it, right? So that's the problem.
Right, but a lot of even people who kind of are in the know, they rarely look past the number of instructions that their program runs as a metric. Maybe they will look at cache misses and so on. And the hardware has got all of this like rich information that's available. and we don't use it, and we don't know how to use it. So one thing is getting the information into the atmosphere and into tools that people can use, and then the other thing is kind of like using that then to go and optimize things.
So observability, what you are working on right now, observability of in Linux kernel.
It's largely the perf event subsystem, which ironically was a subsystem that was, the previous thing was called O-Profile, and O-Profile came about from a person I worked with during my PhD. We were both doing our PhD same year, and they started working on O-Profile because we wanted to be able to benchmark these binary translators. I'm afraid I need to. I've lost because I work at Google. The standard complaint is that I've lost a room.
Okay, no problem. Where people can find you on the internet?
So Fostodon is the place to go.
Okay.
Yeah, that's the best one.
It was a pleasure to chat with you, and
yes.
Thank you, and maybe see you next time.
Yeah, thank you for being interested. I'm always happy to talk. Thank you.
Thank you a lot. Bye.